So, hello everyone, I'm Elena Agostini, and today, as he said, I will present you BitCracker, that is the first password cracking tool for memory devices encrypted with BitLocker. So I would like to introduce you to BitLocker. Basically, it is an encryption feature in all the most recent version of Windows, so Vista 7, 8, and 10. And basically, with BitLocker, the user can encrypt any type of memory device, like your internal disk in your computer, or your USBs, SD card, and so on. To encrypt your device, you can choose among several different type of authentication methods. And during this talk, we are going to focus on the user password as authentication method, because this is the method that we are attacking with BitCracker. So this is an example. Here we are on Windows 7, and I plugged in my USB pen drive, that is a Kingston of 2 gigabytes, and I want to encrypt my pen drive with BitLocker. So I turn on BitLocker on my pen drive. I choose to encrypt the USB with a password. So I just type the password, and then BitLocker starts to encrypt my device. If later I want to access the content of my encrypted pen drive, I just have to type the same password used for encryption. So BitLocker can encrypt my USB, and then it will give me the access to the content of my pen drive, basically. So BitCracker is the name of our project, and for the best of our knowledge, is the first open source password cracking tool for devices encrypted with BitLocker using the password as authentication method, basically. So the aim of BitCracker is to find the right password, use it to encrypt the encrypted device. And after several researches, we found that the best way to do this type of attack is to perform a dictionary attack. So basically, BitCracker takes as input the encrypted device and a list of passwords. And it starts to decrypt the encrypted device, testing every time a different password from the word list. Of course, it's convenient to implement this kind of attack with GPUs, because with a GPU, you can launch in parallel a huge number of threads, each one working on the decryption procedure, but testing a different password. So obviously, it's more convenient to use a GPU instead of a CPU to perform this kind of attack. So to implement this, our attack, we needed to understand the format of an encrypted volume, how the procedures work, how BitLocker decrypts devices, and so on. So obviously, the first source where we found a lot of information is the blog of Microsoft, basically. But we also found two interesting tools that are libd and dislocker. And they are both kind of suite of libraries and tools that the programmer can use to inspect the format of an encrypted device encrypted with BitLocker. So thanks to those tools, we learned which kind of information we can find inside an encrypted device, how we can read inside the encrypted device all of this information. And for example, with dislocker, you can even decrypt your encrypted device only if you know the right password. So dislocker is not performing any type of attack. It's just useful to understand the decryption procedure and all the other stuff of BitLocker, basically. So after our researches, we found that BitLocker for the encryption uses a complex architecture of keys. So during the encryption, BitLocker starts from the sector of the memory device, and it encrypts every sector with a different key. All of those keys are derived from a single key called the full volume encryption key. The full volume encryption key is in turn encrypted with another key that is called volume master key. And finally, the volume master key is encrypted according to the user authentication method chosen by the user. The decryption procedure is basically the same as encryption, but on the contrary, in a sense that the user types the password, then BitLocker starts several SHA-256 hashes, and it combines the result with a final AES, several final AES, and then it decrypts the volume master key. With the decrypted volume master key, BitLocker decrypts the full volume encryption key, and then finally the entire encrypted memory device. So we found that there's no need There's no need to decrypt the entire memory device. We just need to focus on this part. Because if we are able to find a password that correctly decrypts the volume master key, basically you know that the input password was the correct one. So there's no need to keep working on the decryption, basically. So this is the part, as I said, of the algorithm that BitCracker basically implements. And this is the algorithm. So this is how BitLocker decrypts the volume master key. As I said, the user typed the password, then BitLocker applies twice the hash function to the password. And then it starts this kind of big loop of more than 1 million of iterations, where during each iteration, basically BitLocker applies the hash function to a particular structure that I'll show you later. At the end of the loop, BitLocker produces an intermediate key. And with this intermediate key, it encrypts some kind of an initialization vector. And with encrypted IVU, finally, BitLocker decrypt the MAC, actually decrypt the encrypted MAC and decrypt the encrypted volume master key. With the decrypted volume master key, BitLocker computes the MAC, and finally it compares the computed MAC with the decrypted MAC. And if they are the same values, basically, then BitLocker knows that the decrypted volume master key is the correct one, and also that the input password was the correct one, basically. So, okay, now we have the algorithm, but we need to understand where we can find all the information needed during the decryption procedure. So, we did other researches, as I said, thanks to dislocker and libd, and we found that when BitLocker encrypts a memory device, basically it stores some metadata information, headers, and all the information required during the decryption procedure into 3 different full volume encryption metadata blocks. We found that they are 3 just for backup purposes, so 1 block is enough to find all the information. To recognize the starting of a full volume encryption block, you just need to search this kind of particular signature, which represents the starting of the block. Here, this is the image of an encrypted memory device encrypted with BitLocker on Windows 8.1. As you can see here, at the number 1, there's the signature. And then if you keep reading the image, you will find, for example, at the number 5, you will find the salt. You will find at the number 6, the type of encryption of the volume master key, and we found that in case of user password, this type of encryption is always AES-CCM. Then there's the encrypted MAC at the number 8, number 9 there's volume master key, and so on. So we were able to find all the information required by the decryption procedure inside an encrypted volume, basically. So having all of those information, we moved from the CPU implementation of the decryption algorithm to the GPU implementation. And we choose to run this algorithm on NVIDIA GPUs. So I don't know if you are familiar with CUDA environment, with CUDA language, but we started, our first implementation of BitCracker was in CUDA. Of course, we got poor performances. So we had just 100 passwords per second testing on a GPU Tesla K80. So we wanted to improve this procedure in order to speed up the computation and test as much password as possible in the same amount of time, obviously. Of course, this kind of algorithm is limited by the number of instructions, not by memory, bandwidth, or other factors. So we tried to figure out if it was possible to reduce the number of instructions, if there's something that is not so useful, basically. So we start to improve the bottleneck of the algorithm, that is basically the big loop. Okay, so our improvement, as I said, is about the iteration inside the big loop. So during each iteration, BitLocker applies the hash function to a particular structure of 128 bytes. The first part of the structure is composed by 64 bytes, and they hold information about the result of the previous iterations, the values of the fields in the first part. They depend also on the input password, so we cannot predict basically nothing. So we cannot say a priori what's inside this part of the structure. But after the first 64 bytes, there are 16 bytes of salt, and we know that there's just 1 salt for each volume master key. So it never changes, basically. Then there's the counter, that is basically a long integer. And the counter represents the current number of the current iteration. So we basically know for each iteration the value of the counter, because it's the number of the iteration itself. And then there are the padding and the size. They are here in order to be compliant with the standard of SHA for the size of the structure, and so they are fixed, basically. So when BitLocker applies the hash function to this structure, according to the standard, it needs to split the structure into 2 blocks of 64 bytes. And then it starts to apply the hash function to the first block. And then the result of the first application of the hash is used as input of the second hash, basically. During the second hash, BitLocker computes the hash of the second block. And then the final hash is basically the final result of the current iteration, and so on for all the iteration inside the loop. So what we can say here, where we can do something, what we can improve. So looking at the standard of the hash, we know that the first input is used as it comes without any changes. But the second part, so the message on which we have to compute the hash, basically is transformed. So 64 bytes of input message are transformed into 64 so-called W blocks. They are basically they are integers. So every time that BitLocker applies the hash function to one of the 2 blocks of the structure, it needs to compute again all of those 64 blocks based on the input message. But as I said, we cannot predict nothing on the first block, but we know during each iteration the value of the second block. So our first improvement was to start some kind of pre-computation period before the main attack in order to compute all the possible W blocks required during the iteration. This means to pre-compute 64 W blocks for all the more than 1 million of iterations. So this means to pre-compute 67 millions of integers, basically. They required about 256 megabytes, so it's a reasonable amount of memory to be stored inside all of the modern GPUs. So having this pre-computation, during the second application of the hash function, basically, our attack, so BitCracker, it doesn't need to recompute every time the W blocks. It just needs to read the required blocks from memory. In this way, we saved a lot of time because we removed a lot of instructions, basically, a lot of load, a lot of store, and so on. Then we improved the algorithm for the CUDA environment. So we reduced the number of operations. So we could use less registers. We avoid the use of local memory. We improved the occupancy. We use texture memory instead of global memory, and so on. And we also forced the use of particular instructions that are IAD3 and loop3.lut. They are useful starting from the Maxwell architecture of NVIDIA GPUs. And basically, with those instructions, you can perform several logical operations among 3 different inputs, as they would be just as a single instruction. So on a Kepler architecture, those operations doesn't basically change nothing. So the XOR among 3 inputs will be performed by 2 instructions. But starting from the Maxwell architecture, they will be executed by a single instruction. So this represented a huge improvement in performance starting from Maxwell architecture, so Maxwell, Pascal, and also Volta GPUs. So this is the second version of the BitCracker algorithm. So as I said, the improvement was in all the iteration of the big loop, so reading the W blocks instead of computing them. The performance increased from 100 passwords per second to 340 passwords per second on the same Tesla K80 GPU. But we wanted to improve the performance as much as possible. So we started to focus on the second part of the algorithm. In fact, when BitCracker computes the MAC based on the decrypted volume master key, it uses a lot of operation. It performs several times AES, a lot of XORs, a lot of arithmetics, and so on. So we tried to understand if it was possible to remove as much operation as possible. So we found that, according to the standard of Microsoft, the structure of the decrypted volume master key is composed by 44 bytes. The first 12 bytes, basically, they hold information about the key. And the remaining 32 bytes are actually the key itself. So focusing on the first 12 bytes, the bytes 0 and 1, so the first two, basically they hold information about the length of the key. And the length of the key is always 44. Then there are the bytes 4 and 5. They are some kind of version number, but what's interesting is that they are always 1. And finally, there are bytes 8 and 9 that basically they represent the type of encryption of the volume master key. And we know that in case of a user password, the encryption of the volume master key is always done with AES CCM. And according to the standard, this means that those 2 bytes, they can assume a value included in this range. So they can have 6 different type of values, so they are not so much. 6 is not a high number. So basically, our improvement was to remove the comparison of the MAC and check the structure of the decrypted volume master key, like this. So basically, this is the final algorithm of BitCracker. When BitCracker decrypts the volume master key, it basically checks the format of the volume master key. So it checks basically the values of the first 12 bytes of the decrypted volume master key. The performance increased from 340 passwords per second to 385 passwords per second. But of course, this type of check can lead to false positives, because we are not sure. I mean, the only way you can be sure that the decrypted volume master key is the correct one is computing the MAC. But with this kind of fast check, we improved performance, and also a false positive is not as bad as a false negative. So if you have a list of false positives after the execution of BitCracker, you can always run again BitCracker with a particular option that I'll show you later, which forces the use of the MAC. So you can force on a small word list of false positive, you can run again BitCracker, enabling the comparison of the MAC in order to be sure of which one of the false positive is the right password. So this improved algorithm is totally empirical. We verified this algorithm empirically. We tested it with all the possible BitLocker version. I mean, BitLocker on all the possible Windows version. In particular, Windows 10 has 2 different encryption modes. In the compatible mode, there's nothing different with the previous Windows versions. But in the not compatible mode, basically, BitLocker uses XTS AES instead of AES CCM. But we found that these changes doesn't affect the encryption of the volume master key. So basically, BitCracker is able to work with both compatible and non-compatible mode. This is the first chart of performance. As you can see, we implemented also an OpenCL version, so you can run BitCracker also on non-NVIDIA GPUs, obviously. We tested the OpenCL implementation on an Intel Core i7, a quad core. As you can see, the performance on a CPU cannot be compared with any other run on the GPU. But of course, we got the best performance in terms of number of passwords evaluated per second on a Tesla P100. That is one of the newest NVIDIA GPUs having the Pascal architecture. So as far as we know, there isn't another tool or something else that uses the same format of BitCracker. So we needed to understand if we did a good job, if we can do it better. So we needed to compare BitCracker with something else. And we choose to compare BitCracker with Hashcat. So to compare BitCracker with Hashcat, we needed to move to evaluate our performance from the number of passwords per second to the number of hashes per second. So basically, each password requires 2 million of hashes. This means that for the best performance of BitCracker, when BitCracker is evaluated 1,400 passwords per second, its hash rate is about 2,900 million of hashes. Of course, this kind of comparison is not so fair because we use the raw SHA format of Hashcat, while BitCracker has performs a several hash, then an AES, several XOR. Hashcat doesn't have the W blocks improvement and so on. BitCracker is in CUDA, Hashcat is in OpenCL. But what is important of this test is that the performance of BitCracker can be compared with Hashcat. So we did a quite good job. So BitCracker is available online. You can find BitCracker in 2 different places. The first one is our repository in GitHub. And here you will find our standalone implementation, both in CUDA and OpenCL. And this is the most updated version. This is where we release the new code, where we update and we write all the news of the next development, next improvement, and so on. But of course, in our standalone implementation, there's the lack of some cache mechanism, dictionary manipulation, and so on. So to overcome this issue, we released BitCracker as the OpenCL format of BitLocker for John the Ripper. I think that everyone knows where to find the John the Ripper code. This is the wiki page, our wiki page. And you will find that the license is GPL2, but we are totally open to start any type of interesting collaboration. So if you think that BitCracker can be useful in your forensic analysis, or if you want to integrate BitCracker in something else, please contact us. We can start something really interesting. And the last part of my talk, I would like to give you just an overview about how BitCracker works. Of course, this is the standalone version of BitCracker. So the first step is to get the image of your encrypted device. So for example, as I showed you at the beginning, here I've encrypted a USB. And then I need to extract the image of my encrypted USB. So for example, here I'm using dd, that is a command from Linux, but you can use whatever you want. Or if you want to run something, just some tests, or you can want to try something at home, you can just create a virtual hard disk on Windows and encrypt it with BitLocker. It's up to you. How do you want to test BitCracker? Then you have to run BitCracker_hash on the image of your encrypted memory device. This tool will start to check the format of your encrypted device. If it has volume master key, if the volume master key has been encrypted with the user password, and other stuff. So if everything is OK, at the end, it will output this hash. This hash is all that you need to start your main attack. So you don't need to have your image always with you when you want to start the main attack. You just need this hash. And then, obviously, you have to start the main attack. So this is the -m option I show you that I was talking about. So you can choose to run BitCracker with or without the MAC comparison. Without the MAC comparison, it will be fast. Without the MAC comparison, with the MAC comparison, you will avoid any false positive, but of course, performance will decrease. So it's up to you. And this is an example. So here we are not doing performance, it's just an example. This is the CUDA implementation of BitCracker. As you can see, you can choose, for example, the GPU. I'm launching the GPU 0. I'm running just one CUDA block. I want to process just one thread. I want one password for a single thread. So any type of setting. And in the end, BitCracker finds the password, and it output the password here at the bottom of the screen. So of course, as I said, BitCracker obviously attack only the user password method, so we are not able to attack memory devices encrypted with smart card or TPM. But we found that all the authentication methods, they have a common element, that is the recovery key. So when you encrypt your device, BitLocker asks you where you want to store your recovery key. That is basically a 48-digit key. And basically, you can unlock your encrypted device with this key if you are not able to access your encrypted device in the usual way. So let's say, for example, if you forgot your password, or if you lost your smart card, and so on. So we are preparing this attack. The algorithm is quite similar to the user password method. And I think that we are going to release this second attack the next month. So it's quite ready. Then we will keep studying the format. We would like to know if there's some kind of difference if you encrypt your device with TPM or user password. So we need to investigate some more inside the encrypted format. We'll start to implement a multi-GPU solution. So if you have a cluster of GPUs, you can run just a single instance of BitCracker in your cluster. We would like to test on the newest Volta GPUs of NVIDIA and also other non-NVIDIA GPUs and so on. So that's it. Please share our project, test it, open any issue you think that can be useful on the repository. Thank you.
Thank you. We do have time for questions. Any Windows users here? This must raise questions. No, no questions? There's a question.
Oh, okay.
So if the recovery key is generated fully random, what's like the average time to crack it with, for example, one Tesla GPU?
The recovery key, you mean?
Recovery
No,
key,
it's not random. There's a particular algorithm. So we are planning to, first of all, build the entire dictionary. And then you have the dictionary, you know that all of the recovery keys are in the dictionary, and then you can just start the attack. That's it. We are trying to.
Just out of hash reversing interest from myself, how easy would this be to scale up with multiple GPUs?
Yeah, it's this basically you're just running the same executable on more or different GPUs, so the performance are stable. Basically, they're always the same. The same performance I show for a single GPU, they are maintained in all the GPUs that you're running. The executable. So
Just works.
Yeah.
Okay. Any more questions? Yeah.
I was wondering if you, because still the rate is still low compared to OCL hashcat for, I don't know, MD5 or something, right? To make an extreme example. But did you look at, there's a nice paper of training a neural net with leaked known passwords, plain text passwords, and combining that with a genre, with a guest dictionary.
Oh,
so this might speed up things a lot also.
Mm-hmm.
Because
That's
we
an interesting
humans
suggestion.
are, yes, we tend to have sort of the same ideas about passwords.
Yeah. No, I didn't know. It's interesting. But I would like to point you to the performance I showed you before here. This is what, I mean, I know that 140 passwords per second is not so much, but if you see to the hash rate, we cannot do it's better. So that's the point.
Okay. No more questions, really? Looks like it. Okay, then thank you very much, Elena.